Hi, Algebra 2 honor students. This is going to be Algebra Review Day 2 here. So we did a little bit of factoring yesterday. Let me plug in here, and we're going to jump right into some of the concepts that we'll see as we continue talking about some of the main ideas of polynomials, factoring, things of that nature. So if I turn this on, it's going to switch right over. So this is going to be a day of notes by hand. So if you wouldn't mind getting out some paper that you can take some of these notes on, that would be fantastic. We are going to start by having this discussion about ways in which we can multiply polynomials. One thing I'll say kind of quickly at the very beginning here is if you need to pause at any point because something's going too fast, that may very well be the case. Without doing this live in front of a classroom right now, certainly I might go a little bit faster. No one's going to be stopping me to say, hey, I have a question, or hey, slow down. So feel free to pause as needed, and let's get right into it. So the first example that I have here is let's multiply 2x plus 3 times x minus 8, those two binomials. So there are two main methods that I would consider when we're multiplying those two binomials together, one of them being the double distribute, or otherwise known as FOIL method. And some students are very familiar with that term. And then others are more familiar with the concept of multiplying them with the box method of multiplication. So I'll show you both methods just as a recap to make sure that we're confident of how we can multiply these. FOIL is an acronym for first, outer, inner, last. So what that would mean is if I recopy the example, you would do a double distribution where you do the first products there, and 2x times x is 2x squared. Then you would do the outside product. That's going to be a total of negative 16x. The inside product plus 3x. And then the last terms multiply would be minus 24. So that's what FOIL looks like. Maybe you're used to this process, the double distribution there. So then if you combine like terms in the middle, we get 2x squared minus 13x minus 24. And of course, the box method accomplishes the same exact thing. It just organizes the information a little bit differently. So if we make a box here, what I would do is I would put one of the factors across the top, maybe 2x plus 3, and then the other factor, x minus 8, across the bottom here, or on the left column, I should say. And then if I go ahead and I multiply what would go in these corresponding boxes, we get this is 2x squared. X times positive 3 would be 3x. 2x times negative 8 is negative 16x. Negative 8 times 3, at the end there is minus 24. So we get the same result if I combine like terms here, right? So we can combine those two together to get that negative 13x we see in the middle, and we should get the same exact product. So when multiplying binomials, if this is a process that you're most comfortable with, that box method, I'll tell you it's not natural for me because that's not how I learned it when I was a student. So I'll illustrate it here and there, but keep in mind, we should get to the same place in the end, whether we use this FOIL method or the technique of the box method. So here's another question that's sort of similar to that, where we're going to expand 2x minus 5, that quantity squared. And when we do that, you might get something like this to start. So I don't know if anyone started writing this down and did this in their next step. And I better move my camera here to see the rest of this. And then maybe you did this next. No, any takers on this? All right, well, you're going to see my awful math humor come out right now because here we are. We're really expanding it here, guys, aren't we? All the way down to there. So, of course, that's not what I mean by expand, but that's one of many very corny math jokes that you'll see me use this year. When we say to expand this, we're saying, all right, well, when we square something, we know that means to multiply it by itself. And what I'm hoping you're not thinking, although it is a very common student mistake, is to just square each of these, right? Is the answer just 4x squared plus 25? Well, we'll find that it's not if I actually do the FOIL technique. So I'm going to do FOIL for this one. And 2x times 2x is the 4x squared. The outside is negative 10x. The inside is negative 10x. And then the last is plus 25. But notice how these middle terms don't cancel out. Negative 10x minus another 10x gives you minus 20x in the middle. So you really have to be cautious that when you're expanding a binomial like this, when it's being squared, I would recommend just writing it out next to itself, writing down what the product is, and then kind of going from there. So that's what we have as far as maybe just multiplying some binomials go. If we go to another example here, Let's move this up. I'm going to recommend that for this example, you hit pause and then try a technique that you're comfortable with. So the only thing I'll say about this is that it's not really an example of FOIL. FOIL I use for two binomials. This is a binomial and a trinomial. Could we still do some distributing? Sure. But either try distributing through and combining like terms or do the box method and then check back in, hit pause, and then check back in in a few seconds here to see if you get the correct answer. I'm going to actually right now reveal what the answer is. Here's my method I did box method for this one. When the polynomials get larger, it is a really nice way of organizing the info, especially with these diagonals of like terms to combine. So that might be a technique that you want to use for something like this. So when we combine like terms after using the box method, the resulting polynomial is this cubic polynomial, x to the third minus x squared minus 8x plus 12. Okay, so if we're feeling pretty good about that, we're going to move on and talk about the concept of an identity. And identities are something that come up in a variety of instances in this course and other math courses, but it's an equation that is always true. Okay, so we know that some equations are only true depending on the value of x. But an identity is always true no matter what we sub in for x. So here's an example of an identity. We know that x squared minus y squared is always equal to x plus y times x minus y. But I'll give you a non-example. A non-example would be x plus 2 equals 5. Because that's not always true. That's only true if x equals 3. Whereas this is always true no matter what we sub in for x and y. Okay, so something that's always true is going to be an example of an identity. So what we're going to get into is something called proving that something's an identity. Here's an example of what we're going to do. We're going to take a look at a to the third plus b to the third and prove that it equals the product of these two. So how am I going to prove the identity? Well, it's not going to be like a geometry proof from last year where we have statements and reasons. It's going to use the technique of polynomial multiplication. So all we're going to do here is actually multiply these polynomials together and prove that it equals a to the third plus b to the third. Since I use box method in the example above, maybe I'll do some distributing here to show you what that would look like, and then I'll distribute the b across, and we're going to get 6 terms all together here. So we're going to get a to the third to start. The next term would be minus a squared b. Then we're going to get plus ab squared. Now I'm going to distribute the b across. I could write this as plus ba squared, but I'm going to keep the a out front always so that I can see if it has any other like terms to combine with. So I'm going to write the next term as plus a squared b. Then in the next term, it would be minus ab squared. And at the very end, plus b to the third. So that's what the distributive property would look like here. And then if we think about combining like terms, notice how we do get a bunch of things to cancel out. The minus a squared b, the plus a squared b, ab squared and negative ab squared. So we are just, in fact, in the end, left with a to the third plus b to the third. And thus we've proven the identity. It sounds like a really intense process of prove this mathematical identity. But in a sense, all we really had to do to prove the identity was do some multiplication. When we get later in the year, we deal with other types of identities. There might be a little bit more involved than just doing some multiplication.
Good morning, Fifth High School. We're going to start in the auditorium in about 7 minutes. Again, we're going to start in about 7 minutes in the auditorium.
Sorry for the interruption there, guys. But let's move on, actually, and I have one quick note at the bottom. It's up to you if you want to copy this into your notes. But when proving an identity, you can only work on one side of the equal sign at a time. If you cross the equal sign, you are assuming the two expressions are equal. But that is what we're trying to prove. So when I say prove that this is an identity, this equal sign is kind of a question mark right now. I don't know that they're really equal until I've done this work. So in other words, what I'm trying to say in this note here is you can't, to get started, subtract b cubed from both sides, because then you're assuming that they're already equal. You really can work down the left side. So I like to draw a wall sometimes. I'll draw a wall right where the equal sign is, and I can do some work on the right algebraically. I can do some work on the left algebraically. But at the end of the day, we have to make sure that we don't cross over this wall. Okay, I can't subtract BQ from both sides when proving an identity specifically. I know when we solve equations, we can cross that wall and do things like that. But be careful that when you prove identities are true, you kind of just work down one side only. Okay, and it's typically pretty obvious to see which side we should try and simplify. So that was just a quick note about that. All right, moving on from there, we're going to do a little bit more factoring today, and then that's it for Algebra Review Day 2. So here's an example where we have x plus 3 squared minus 7 times x plus 3 plus 10. So in this example in particular, you may be tempted to do what we did earlier today and expand this and square it and maybe distribute the -7 and clean things up here. But I might try to convince you that maybe that's not the easiest way to do something like this. So although that's not wrong, squaring this and distributing the -7, cleaning it up, factoring it, what if we consider that this quantity, x plus 3, we see it twice there, right? Once being squared, once next to the -7. What if we replaced it with a different variable? So what if I said, let A equal that quantity x plus 3? This process of replacing that binomial with a single variable here is known as using what's called, and this is not mean, it's mathematical, guys. It's known as using a dummy variable, or you might hear teachers refer to this as substitution. But if you hear me refer to a dummy variable, that's what I'm talking about. Just plugging in a variable just as a placeholder for now to make my job a little bit easier, because then look at what this turns into. A squared minus 7a plus 10. Cool, I know exactly how to factor that. Maybe it wasn't as obvious in its original state, but this is something that I can figure out things that multiply to 10 and add to -7. So that's going to be a minus 5 and then a minus 2. All right, do not forget though, if you're going to use a dummy variable, you have to replace a with what it equaled up here. Okay, so now at this point in the process, we're going to go ahead and say, oh wait, but a was really x plus 3. So go ahead and resub that back in. And now that we have that, combine like terms. Well, wait, 3 minus 5 is really the same as x minus 2. And 3 minus 2 over here is the same thing as x plus 1. So it's not to say that if you went back to the original that you wouldn't have gotten the same result had you done some algebra up front there. But using a dummy variable can really simplify the process in a lot of cases and make your job a little bit easier. Here's another example that we'll try, and maybe we'll think about dummy variable for this one. Whenever you have a quantity in parentheses, a binomial squared, or if you see that binomial repeated in the expression, it's probably a good idea to consider using this dummy variable technique. So for example, 2 here, I'm going to let, I don't know, pick your variable out there. I'm going to choose j this time, equal the quantity x minus 2. Here's what I hate when students do. I shouldn't say hate, but I really do hate it. Sometimes students say, let x equal x minus 2. Well, boy, does that get confusing. Because if you let x equal x minus 2, in the end, you're going to think you're done when you factor and you have x's in your answer, but you're probably not done. Okay, so be cautious about that. Try not to choose any of the other 25 letters, other than x in this case. Okay, so if I have j squared minus 100y squared, this is the difference of perfect squares, so it's going to be j, and then plus 10y, and then j minus 10y. So once I've done that, just don't forget to resub in what I know j is. J is really x minus 2. And by the way, when you plug in that quantity x minus 2, notice how I'm not plugging like a double set of parentheses around that. If you do, that's fine, but it wouldn't affect the way I write this end expression here. Whether I put the double parentheses here or not, it wouldn't affect the way my final answer looks. Okay. So let's just try one more of these, and then we'll say that that's it for today. All right. So we'll do a few more of these in class as practice, but the last one we'll do is example 3 here. So I'll let you use x this time. Let x equal the quantity a plus b. So now this is going to turn into 2x squared plus 4x minus 6. And the first thing I'm hoping you're thinking about here is when we factor, we must think about GCF first. It's the first technique you really should consider so that something's factored completely. And then, hey, you can take out a GCF of 2, which is probably going to make our factoring go a little bit easier. So when I take out that GCF of 2, now we can factor this into x plus 3 times x minus 1. And don't forget about that very last step. We used x as a dummy variable, but it really represents a plus b. So the final answer would be 2 times a plus b plus 3 times a plus b minus 1. This one I think would have been tougher if I didn't use a dummy variable. If I tried to like distribute all that out and figure out how it factored, it probably would not be as simple as I just made it in this example. So we'll certainly do a little bit more with this dummy variable technique and some other algebra practice as we move on here. But if you have any questions, certainly let me know. Thanks, guys.